All right, so in the last video, my pencil ran out of battery, so let's continue. So the question now is the question that we can also ask is, what is the probability to measure a certain value of momentum, P. And so the generalized statistical interpretation of quantum mechanics now tells us really that the probability density for measuring specific values of momentum P is given by Fp psi squared, so by C of P squared, or C of P absolute value squared. Okay, great. The second example is, let's look at position operator X. So let's see what we get here for the eigenvalues and eigenstates. So now the eigenvalue equation for X is, we're looking for some function that I denote here by G underscore X, that's equal to X times G of X. So that's the eigenvalue equation. And we'll work backwards for this example. So what do we know? For a state psi, we know that the probability density to find a particle at a given position x0 is given in terms of the absolute value of the wave function squared, that corresponds to this quantum state psi. We know from the generalized statistical interpretation that we should be able to write, so we know that we can write that this should be equal to, or this probability density should be equal to the absolute value squared of the inner product of the eigenstate to the position operator at corresponding to position x0. So the inner product of that eigenstate with psi absolute value squared should give me also this probability density. So what we want is a function in real space where the inner product of that function with the wave function psi of x gives us the wave function at position x0. And looking at this, the function that would fulfill this is the Dirac delta function in real space. And this kind of makes sense since, the Dirac delta function seems really, or is really, a function that corresponds to, corresponds to a definite position. Let's think about this much more. Not much more, let's think about this a bit more and test if the eigenvalue equation actually is fulfilled. So does the Dirac delta function actually fulfill the eigenvalue equation, which would be x, g x naught x is equal to x naught times g x naught of x for all values of x, so at any position x. And the answer is yes, it does, since delta x minus x naught is only non-zero exactly at x equal x naught. So we can write that x multiplied, or position operator multiplied with a function that always multiplies the function just with position x. That's the first step. But then we can simply, substitute the general x here with x naught, because our function here is everywhere 0 apart from at exactly x equal x naught. Is g of x naught of x normalizable? The answer here is again no. Even though the area under the delta Dirac delta function is equal to 0. The delta function is actually not square integrable. So if I take the square of the delta function, which I would need to do to normalize it, I can't do that. So it's not square integrable. And so in that sense, we have the same problem with the eigenfunction of the position operator as we have for the momentum operator. There, the eigenstates were also not normalizable. However, g of x, just like the eigenstates of the momentum operator, these eigenstates are again what we called just before Dirac normalizable. So if I take the inner product of two of them, g of x dash and g of x, this is actually equal to the delta x minus x dash. And that again guarantees us that we can represent any quantum state that we want in terms of these eigenstates. A few final observations on this topic, a few more observations. We've seen that the eigenstates of P and X are actually not part of the Hilbert space. They can't be normalized. But a family of their linear combinations. Oops. What do I mean with this? Well, this means we can, even though the eigenstates of P and X themselves are not part of the Hilbert space, we can use the eigenstates to represent or build quantum states that actually are within the Hilbert space. And so one example, for instance, is again, for instance, the Gaussian wave packet that we can build out of the eigenstates of either the momentum or the position operator. And this is, by the way, and you might learn this later, this is a general feature of Hermitian operators with continuous continuous eigenvalues. So it's not necessarily special to position a momentum operator, but if you come up with other observables that have continuous eigenvalues, you will see the same properties. And again, I guess I said this just before, eigenstates of P and X are very useful, though. We have seen this actually when we studied scattering in one-dimensional potentials and wave packets. Okay. Another observation is that the proofs that we've done, the proof that eigenvalues are real and eigenvectors are orthonormal, does not work for continuous eigenvalues, or more precisely for observables that have continuous eigenvalues. In fact, a Hermitian operator with continuous eigenvalues can have eigenvalues that are not real. And an example for that is, for instance, take just the real exponential, so f of x is equal to e to the kappa x. If we apply the momentum operator to this, then in the real state representation, that is this derivative. And, if we take the first derivative of an exponential, we get the exponential back. So this just gives us h bar divided by I times kappa f of x. And meaning that this f of x here is an eigenstate to the momentum operator, and this is an eigenvalue. And so here we have found that we found an imaginary eigenvalue. But we will only work in quantum mechanics, or the only ones that are physically relevant are the eigenstates that are physical. So eigenstates, when the eigenstates with real eigenvalues, because imaginary eigenvalues to physical observables are not physical, because we can measure the eigenvalues, and what we measure got to be real. Okay. And this pretty much brings me to the end of this discussion. A fun exercise that you can think about yourself is we have, seen that the representation, or that the eigen eigenstate to the position operator is given by the direct data function in real space. We have seen that the eigenstates to the position operator in real space is given by 1/2 pi square root over 2 pi h bar e to the I px divided by h bar. You could ask how what is their representation in momentum space. And that essentially would be the question of, if I have gx of 0, that means, I can write this as a function of minus infinity c of p f p dp. And so what is this c of p here? And then this c of p here is the representation of, the eigenstate of the position operator, but written in the momentum representation. So maybe you can work that out.